Hello everyone. We are going to talk about uh, hello everyone. We are going to talk about numbers in a very brand new way. I believe no one really viewed numbers this way before. So let's start from the very beginning, where the fundamental theorem of arithmetic states that every number n can be written as a multiplication of prime factors. So 2 at x times 3 at y times 5 at z, and so on. And this representation is unique. So for example, if I have the number 18, yeah, it is a very ugly 18, then I know that it can be written as 2 to the power of 2. Oh, it is not. Yes, I already made a mistake, which is not a big problem because I have an eraser. So it's 2 times 3 to the power of 2. While, for example, the number 12 is 2 to the power of 2 times 3. Yeah? That was in my head, so that was the problem. Okay. The statement is that this representation is unique, so I cannot write 18 as the multiple of 5 or 7 or whatever, and it holds for every integer. Well, if it is a unique representation, we can just leave out the prime numbers, and the xyz will be the unique representation itself because there is no additional information in the 3, 5, or 7 as a basis. So the number 18, therefore, can be written as 1, 2, and infinitely many zeros. While the number 12 is 2, 1, and infinitely many zeros after. If we only focus on the first two prime numbers, then, and here comes the new view of numbers, we can represent every number as by their coordinates in an infinite dimensional space. So let's start by setting up our coordinate system. And in this system, the x-axis is the 2 at x, and the y-axis is the 3 at y. So at 1, 0, we have 2. At 2, 0, we have 4, and then 8, 16, 32, 64, 128, and why would I continue? Then we have 3, 9, 27, 81, and here we are going to have 6 because this is 1, 1, which is 2 times 3 equals 6. This one is 4 times 3, 12, and this one is 24, 48, and as you can see, I can easily continue this further to the right. This one, 18, and 36, 72, 144, 54 here, 108. Okay, you got the point. What is really interesting in this representation is that here I have all the numbers that have 2 and 3 in their prime factorizations. But every other number that has anything else is not in this plane. To place them, I would need the number 5 in a 3D direction. Well, there would be 5, 25, 125, and in this 3D space, I could just place all the other numbers. I'm just removing it because it's not nice. But let's focus on this plane only first. What do we have here? Let's try and use a different color first and highlight number 12. Number 12 is in a rectangle, and this rectangle has 6 points. What are the 6 points here? Oh, by the way, the 0, 0 is 1. So these 6 points are actually all the divisors of 12. 1, 2, 4, 3, 6, 12. 12 has no more divisors. These are the only divisors. And the same applies to number 18. It also has only 6 divisors, which are 9, 18 itself, 3, 6, 1, and 2. Okay, it's interesting. It gives a very good insight. But let's see one more very interesting point here. Number 6, the crossover for these two rectangles. Number 6 is the greatest common divisors for number 18 and number 12. And it's fascinating because this fact holds for infinitely many dimensions. So currently we are only focusing on these 2 dimensions, but if we would extrapolate or use other prime factors, we would still have the same rule that the intersection of the 2 n-dimensional hyper cubes has their outermost point. So we are talking about this common rectangle of the 2, and the outermost point of that is the greatest common divisor. And if we have a covering rectangle, the outermost point of the covering rectangle is number 36, which is the least common multiple of these 2 numbers, so number 18 and number 12. And it holds for everything. So if I would have chosen number 24 and 18, the least common multiple would be 72. You can easily check it, but the least common divisor would still be 6. The greatest common divisor would still be 6. So this alone shows that this representation is very useful to think about numbers. But there's more. So if I just remove everything, staying here, and I check what happens with a number if I add the vector of 12 to it. Let's say I do here. The point for the number 9 plus the vector of number 12 arrives to a number of 108. And 108 is incidentally 12 times bigger than number 9. What happens with 3? Oh, the same. We just multiplied by 12. Does it work outside of this area? Let's see here. 4 times 12, 48. So we have a multiplier vector. We can simply multiply any number with a vector. And again, it holds for any dimensions, not just 2. This is a very beautiful stuff. What happens, however, if I subtract? So let's say I'm using our baseline as number 2. Subtracting it from 48, 24. Dividing by 2. Dividing by 2. All right, what happens here? And that becomes even more interesting because this is 3 over 2. If I use this point, 1 over 2. And if I choose the number 3, I can get divisor by 3. So I have 4 over 3 or 1 over 3. And as you can see, all these data points are still on our grid, on our very nice grid that goes through the whole numbers of this plane. So, in conclusion, every rational number oh, that was the real number. Every rational number. So, in conclusion, every rational number is in the whole coordinates in this plane. And every whole coordinate in this plane is a rational number. So we can see how dense or rare the rational numbers are. Okay, let's go back again. Sorry, it takes a bit of time. Here we go. All right. What happens, however, if I not add a vector, but multiply a vector? Let's see if I start with the vector 6, for example. If I multiply it by 2, I will reach this point of 216. So 216 is, in fact, 3 to the power of 6 to the power of 3, which means that multiplying a vector by a given number means that we are exponentiating the given number that the original vector represented. Yeah, it's 216, sorry. What happens, however, if we get the inverse function of the vector multiplication? We get vector division. So let's say I got the vector of 8. I got the 1/3 of it. I get to number 2. So 3 third root of 8 is actually number 2. What happens, however, if I start from a vector that is not divisible by 3 or 2? So let's see what happens with the number 2 if I get it, if I divide it by 2. I reach to a point that is square root of 2. So here, in the middle points, I have all the numbers lined up over the x-axis. I can reach them by dividing by 2, or I can even get to the pi, which is around here. But wait a minute. The same applies to this one. So I can even find the number 2 here, which was here originally. Let's clean the picture again a little bit. So basically, I have the number 2 here. 2, because that was 1. Okay, how can it be? The original statement was every number can be written as 2 at x times 3 at y times whatever. But if we generalize this equation, we can rewrite it as n equals 2 at x times 3 at y in this plane, but I don't need x and y to be in the whole numbers. So if I choose x and y freely, I can find an equation, I can find a solution where x and y, chosen wisely, gives back number n for any n. Okay, write it down a little bit differently. So logarithmic of n equals logarithmic of 2 at x times 3 at y. Logarithmic of n equals logarithmic of 2 at x plus logarithmic of 3 at y, which means that logarithmic of n is actually x times ln 2 plus y times ln 3. I write it here more clearly. Ln n equals x times ln 2 plus y times ln 3. What is it? This is the equation of a line. And the line itself goes through these 2 points, so it must be something like that. This is actually number 2. Originally, we thought that this is number 2. However, we found that the number 2 is a whole line in this 2-dimensional space. This is a very interesting thing here. Okay, let me open up Desmos and show you a proper equation here, because my lines are just ugly. So as I promised, I opened up Desmos, one of my favorite tools on the internet, and here is the equation I was talking about, this one. What you can see here is the red line showing the equation where A in this case is equal to 2. Let's see what happens with 3. You see, it goes through there. 4, 5. Wow, that's interesting. 5 has no intersection on a whole coordinate in this system. Never. So it has no intersection here, here, here. This number itself is not divisible by 2 or 3. 6, there you go. It goes through the line, the cross at 1, 1. 7, nothing. 8, 9. You see the blue number on the top here. 10, 11, 12, 13, 14, 15, 16. All right. And look at how slowly it's moving. So number 36 is just that far away, while number 6 is this far away from the origin. So number 36 is just 2 times further, or not actually 2 times further, but roughly 2 times further in this diagonal than number 6. Actually, if I show this line, you can see the real distance of each number from the origin. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, less and less far away from the origin. And what is the real distance? You can see it here. This is the equation for the distance from the origin. And one more interesting fact that comes from this representation is that the prime numbers can be generated not just the usual way, but this way too. So first off, we need number 2 because it cannot be placed in the 0-dimensional space, which comes from number 1. Then number 3 must be a prime again because the original line for number defined by the first prime number 2 has no whole integer representation of the number 3. Therefore, we must create a new prime number, which is number 3. Then we go through number 4. Number 4 can indeed be represented as a whole integer in this space, so we don't need a new prime number. Then number 5 comes, and as we can see, it has no place in this plane. It doesn't have a whole integer representation, so we need a new prime number, which is number 5. Number 6, however, fits into this space, so we don't need the previously created 5 to represent number 6. 7, again, need, because we know it from fact, but if we would look at the 3-dimensional representation and the hyperplane, which is actually the plane representing x times logarithmic of 2 plus y times logarithmic of 3 plus z times logarithmic of 5 equals logarithmic a, would not have a whole integer cross on this grid. So we would need a new integer, new prime number, which is 7. 8, again, a whole number coordinate. 9, a whole number coordinate. 10, we don't see it, but it could be represented as 2 times 5 again. And the plane itself would cross the new plane defined by the number 2 and the number 5 at 1, 1 again, and so on. So this new way of looking at the numbers gives us a very nice insight. Why do we need as infinitely many prime numbers? Because by moving this hyperplane over this infinitely increasing dimensional space, we will always find numbers that doesn't have integer, whole integer coordinate crossing with the plane. There you go. I hope you enjoyed it. Maybe see you next time.